So in this video, we're going to introduce the idea of a tensor, which might be new to you. But before we do that, let's review a few things about vectors. So here's an xy coordinate system in 2 dimensions, and we define a vector simply as an arrow. So previously we talked about a force vector, and we'll put a little arrow over to denote that it's a vector. And we talked about it being an arrow because a force points with both a magnitude, right, the strength of the force, and a direction. Is it pushing this way or is it pushing that way? Another way we can write it is a column where each entry denotes how far along that axis in our coordinate system it is. So for example here, the number that goes in the first part looks like it's about 5. If this were our units, I go over here and project to the y-axis. It looks like we're about 3.5. So there's our vector. And in 3 dimensions, if we had this arrow pointing out of the page also, we would have a third component. So hopefully this is a familiar idea at this point. But the main point here is that we can represent the vector as an arrow or as a list of numbers. Another thing I want you to recall is something called the dot product or the scalar product. And so let's say that we had 2 arbitrary vectors. One was called f, and we'll do this in 3 dimensions. So it had components a1, a2, and a3. And we had another vector, g, and it had components b1, b2, and b3. So now if I took the dot product of these 2 vectors, f dotted with g, the way we compute that is that I take each element here and I multiply it. So the first element multiplies, the second element multiplies, the third elements multiply, and then I add them up. So the dot product takes 2 vectors, right, which is composed of 3 numbers, down to a single number or a scalar. So the dot product takes vectors and converts it to a scalar, which is just this sum. Another concept is that of the normal vector. So the normal vector is nothing more than if I have a surface of some arbitrary orientation, such as this, that the normal vector at any point always points 90 degrees, so it's always perpendicular to the surface. So over here, the normal vector might be tilted a little bit, and it's always of magnitude 1. So we can illustrate the normal vector with a little foam block here. So here I have a foam surface, and I've colored the surface orange just so we can see it. So let's look at what the vector is at the places that I've kind of marked with an X. So right here, just take a pen and I shove it in. Here, I take a pen and shove it in. Here, I take a pen and shove it in. And everywhere, that vector should be perpendicular to the surface. And you can see that I've curved this surface too. So if I wanted to look at the normal vector here, I would need to kind of tilt it up a little bit because I want it to be perpendicular everywhere around. So no matter what way I look at it, this plane, or this plane, or this plane, that it's always perpendicular to the surface. And so as a simple example, if I had a surface which was inclined at 45 degrees, and I wanted to write out the normal vector, well, we know that the 2 components of that vector are equal, so the x and y components are equal. So 1, 1, 0. And I'm just putting a 0 here because it's in 2 dimensions, so of course I could do this in 3 dimensions as well, or I could leave it off, right? If we were always working in 2 dimensions, I could just call it 1, 1. But we also want the normal vector to be normalized so that its magnitude is 1. The magnitude here is 1 squared plus 1 squared, and the square root of that, so square root of 2. So I would just divide the whole thing by the square root of 2. Okay, I went through that relatively quick because I'm assuming these ideas are familiar to you, but they'll be helpful now that we introduced the idea of a tensor. So here I have a foam cube of material. I colored the sides just so we can see the difference. And what I want to do is describe the state of stress on this little cube of material. And we kind of know that we can do a few things, right? I can squish it this way. I can squish it this way. I can squish it this way. So there's 3 components of squish. But there's also components of shear, because I can shear it this way, I can shear it this way, and I can shear it along that surface. So there's 3 components of shear as well. So a vector seems insufficient here. And it is because not only do we have 3 dimensions of forces, because I can come to any force here and I can push and any direction that I want, but I also have three faces. So not only do we have to worry about which orientation the stress is, but what orientation of the cube that we're talking about is. So here's my cube, and we need a coordinate system here. So I'm going to define this direction as x, y, and kind of out of the plane as z. Each of these faces has a normal vector, right? So here, the normal vector points out that way, here, that way, and here, the normal vector points upwards. And so with our little cube element, we can represent that with our push pins. So there we go. There's our three normal vectors. Okay. So now at each face, we can also represent the forces or the stress that is acting on that face. So here, I have a force which is coming out of the page, which I'm going to call T, and I'm going to use the notation XX. And the X means that it's on the face where the normal vector is pointing in the X direction. And the second index here will denote it's the X force. So I also have a force pointing upwards here that I'll call TXY, because it's the X face, but the Y component of the force. And then a force coming here that I'm going to call TXZ. So these three forces all have the same first index because they are all acting on the face where the normal vector is pointing in the X direction, hence the first X, and then it's the X, Y, Z component of the force. Likewise, on this face, I have a similar thing. Here I have T, Y, Y, where the first index is this is on the face where the normal vector points in the Y direction, and it's the Y component of the force. And then likewise, I have TYX and TYZ. So these are all acting on the Y face, so the first index is Y, and X, Y, and Z forces. And then finally, I think you get the idea, but let's go ahead and draw it out. We have this face as well. So I have TZX, so it's the Z face, X component of the force, ZY, and ZZ. So let's come here and just look at one of our faces, and now rather than using the push pins to represent so now if we look at our little foam block here, rather than using the push pins to represent the normal vector, here I'm using the push pins to represent the vectors for the forces or the stress, really, because remember, we're really just interested in the force per unit area. So this is TXX, TXY, and TXZ. So there we have it. So pretty cool, right? And so the way that we'll write this out is as rather than just a list of numbers, as a little matrix. So our matrix, which I'll call T, is going to have components that look like this. Which is written out as a little 3x3 matrix. And so what that means is that each row here denotes what face we're talking about, right? So is it the face with the normal vector in the X, Y, or Z? So X, Y, or Z. So the X face is blue, Y face is green, Z face is red. And the column here, which column we're in, is going to denote the component of the force or the stress acting. Are we talking about the force in the X, Y, or Z direction? So you can kind of see from this structure here that the elements here on the diagonal, XX, YY, and ZZ, are our normal forces, right? So the XX force, YY, ZZ. All the off-diagonal components refer to shear, right? Because now XY is a force that's acting in this direction on this face. So you can kind of see that the off-diagonal components are shear, the on-diagonal components are tension and compression. An important concept to understand is that when we're talking about the stress tensor, we're really talking about what the state of stress is at a point. And so the way we often refer to this is we imagine that we're taking a little kind of infinitesimal cube of material, and then we isolate that cube and look at it over here. So now we've blown up our little cube of material here, and then we come in and we start talking about the forces that are acting on these faces of this cube. And so this diagram here, where we're drawing the forces on the different faces of the cube, can be a little bit confusing and a little bit misleading, because we're really talking about shrinking this thing down to a point where these vectors are not kind of separated in space, but they're really coincident, right? So we're really talking about the stress tensor evaluated at a point. In the next video, we'll talk about how the stress tensor can vary from point to point. And so on this face here and this face here, the forces don't necessarily have to be equal. The whole cube has to be in equilibrium, but that doesn't mean we always have equal and opposite forces across the face. And so it's important to remember that these forces, even though we draw them kind of separated by the faces, they're really coincident at kind of the center of this cube. So really talk about shrinking this cube truly to zero. So another way to see this is, rather than draw a cube or to think about a cube, think about three planes that are intersecting, right? So here I have an X, Y, and Z plane. They're intersecting at the point. So the stress tensor is really defined at that point right in there. And again, we have a normal vector pointing the X, Y, and Z directions. And on each of these faces, we can have X, Y, and Z forces. But we're really talking about shrinking this element to a point. It's just more convenient to draw it on a cube like this. So it's kind of a subtle point, but it's often a point of confusion that we really talk about the stress tensor here. They're not truly separated by kind of a physical distance, but we just use this cube because it's convenient to write it. Okay, so let's consider this structure here. A person is standing on a beam. I'm going to go to some random point on the beam here, and I'm going to assume that by magic I know the stress tensor. So in a real problem, these would be numbers. Now, just as a notational thing, if I were typing, I would normally use a boldface capital letter to denote a tensor. So I'd write this in bold. It's a little hard to do that when you're writing on paper. So sometimes what I'll do is I'll put kind of two lines underneath it to denote that it's a tensor. Okay, but again, let's go back and let's say, okay, so now we know the stress tensor at this point by magic, or maybe we've done some sort of finite element analysis. And now I want to understand what the stress is acting on a surface going through that point, but inclined at some kind of arbitrary angle. So let's say I wanted to know that surface right here. How would we find that? So the way we do it is we take our surface, any arbitrary surface. I'm just going to draw it kind of curved here. And here's our point where we know the stress tensor. And so the first thing we do is we draw our normal vector. So we have to know the normal vector. So again, the normal vector points right out of that surface at 90 degrees. And if I want, now I want to ask the question, what is the stress or the stress vector acting at this point? So I'm going to call this the stress vector, because we know at this point this could be, I don't know, it could point in any direction we want, right? Because at this point the stress is just a force per unit area that has a magnitude and a direction, right? So if it were all shear, it would be aligned with the surface. If it were all normal, either tension or compression, it would be pointing in this direction. But the stress vector at a point can point in any direction. So the stress vector here is going to equal the normal vector taking the dot product or the inner product with the stress tensor. So what does it mean to do in dot vector dot tensor? So what it means is we can think of this kind of like we would a matrix vector multiply in linear algebra. So what that means is our stress vector, I'm going to write the normal vector here as components, so in x, in y, in z, and it's just going to multiply by my tensor. So now I would just do a matrix vector multiply. The result would be a vector with three components of the normal vector times the tensor. So let's work an example with some numbers just to make sure we understand how to do this operation here. So now let's do an example where by magic I know my stress tensor and it has the values 1, 2, 3, 4, 5, 6. Now you'll notice that I've structured this in a particular way where I repeated the 2 here, the 3 here, and the 5 here. This is what we call a symmetric matrix because if I interchange the rows and columns, I get the same result. Now we'll show in a later video that the stress tensor is always symmetric. And so again, over here, these forces are right there. There's 1, 2, 3. Acting on my y face are 2, 4, and 5, and acting on my z face are 3, 5, and 6. So there's my 9 components of the tensor, but by symmetry, we're going to find that it's really only 6 unique numbers. So 1, 2, 3, 4, 5, and 6. Okay, but now what we want to do is find what is the stress acting on a surface. So let's take our cut in our beam was at 45 degrees, and we want a point right here. So again, this is a slice inside the beam where I've isolated a surface that looks like this, inclined at 45 degrees. Our normal vector is going to be pointing perpendicular to the surface. So in this case, I've drawn, and let's assume that our surface is 2-dimensional. So our normal vector then is going to have 0 in the z component. So it's going to look like 1, 1, 0. And again, the 1, 1 is just because it's 45 degrees, 0 because it's only pointing in the xy direction. But this isn't a true normal vector because its magnitude is not 1. So I need to divide this by its length, which is the square root of 2. Now let's find what the stress is acting at this point. So the stress acting at this point will be a vector because the stress is like a force. It's acting with a magnitude and direction. And so as we saw, the stress vector, is just n dot t, so let's write everything out. I'm going to keep the square root of 2 outside the normal vector for now because it makes it convenient. And now each component of the stress vector is just going to be given by the vector that results when I do a vector times a matrix. So the first component, the x component, will be given by the normal vector taken as the dot product with this column here. So 1 times 1, 1 times 2, add them up is 3. So 3 divided by the square root of 2. So that is the x component. The y component will be given as 1 times 2 plus 1 times 4 plus 0 times 5. So that's 6, also divided by the square root of 2. So that's the y component. And the final one is 3 times 1 plus 5 times 1 times 6 times 0. So 8, also divided by the square root of 2. So we get it just by a simple matrix vector multiply. Should the normal vector be oriented as a row vector or a column vector? Should it be on the left and the right of the matrix? In general, when I have a matrix where I have a vector times a matrix or a matrix times a vector, I don't necessarily get the same result. But in this case, we actually do by symmetry. So if I do stress tensor times normal vector, and I think of it as a matrix times a vector, and again, my normal vector has a factor of square root of 2 in here that I'm just kind of factoring out for simplicity, you'll see that we get the same result. Right? We get 3, 2 plus 4, 6, 3 plus 5, 8, all divided by root 2. So you see I get the same components as before for my vector. So there's confusion about whether the normal vector should be a column or a row, whether it should be left or right multiplied with the matrix, is often a point of confusion and one that often confuses me. But our saving grace here is that due to the symmetry, which we'll explain where that comes from later, but the fact that this matrix always has to be symmetric means we get the same result. So now that we have the concept of the tensor in place, we'll go and we'll start to analyze our equilibrium equations in a more general sense than we've done to date. But the important thing is that the tensor is really just a kind of convenient box, a little 3x3 box that allows us to describe the state of stress. We have 3 rows because we have to worry about what face the force is acting on, and we have 3 columns because we have to worry about whether the force is acting in the x, y, or z direction. So therefore we need this little 3 by 3 box to keep our numbers in, whereas for a vector, a little 3 by 1 box is all we needed. And again, and we'll prove this very shortly, even though we have a 3 by 3 box with 9 numbers, we're going to have a condition which really means there's only 6 unique numbers because these values will be repeated. But let's save that for a later video. That's